Do you remember our video on stack and heap memory? If not, then check out this video first. In that video, we spoke about how stack memory is faster but heap memory gives you more flexibility in storing data. All fixed-sized primitive data types store their values on the stack, whereas dynamic collections store their metadata on the stack and their actual contents on the heap. But is there a way for a programmer to explicitly choose to store the data on the heap, regardless of its default type? The answer lies with the smart pointers. So what is a smart pointer? A smart pointer is a data structure that acts like a traditional pointer, but it also comes with some extra capabilities, like managing the memory automatically. While a regular reference only points to a memory address, a smart pointer owns the data it points to and cleans it up automatically when it is no longer needed. Smart pointers are able to do this because of two core mechanisms, and they achieve it by implementing two special traits from the Rust library. First is the deref trait. This allows the smart pointer to behave like a regular reference, meaning you can use the star operator to access the underlying data. And the second is the drop trait. This helps to automatically free the heap memory when the smart pointer variable goes out of scope, preventing memory leaks without requiring a garbage collector. There are a number of smart pointers in Rust, but in this video, we'll be talking about box. To declare a box smart pointer, we can just write box new and then the value. See this, I have written an integer as a value, which is a primitive data type. So it should be stored in stack. But here, using box, it is actually stored in heap, and the pointer to the heap location is only stored in stack. So no matter how big the content in the heap is, the size in the stack remains constant. How can we validate? Let's check with this example. First, we imported the size of and the size of val functions. The size of function returns the total byte size of raw data type without needing an instance. And the size of val is used when you have an instance of an object and need its dynamic memory size. Next, we have three variable instances with different sizes. StackNum holds a fixed i32 value. BoxedNum holds the same value but in heap using the box smart pointer. Next, we have BoxedArray, which is storing an array with 1000 elements. This is the largest value among the three, but using the box smart pointer. We are then printing a few lines using all these functions and variables. Let me run it and then I'll explain the rest. Okay, so first set of output lines shows the stack sizes for each of the variables. The size of stackNum is 4 bytes because i32 is always of size 4 bytes. The size of BoxedNum is 8 bytes. So if you are wondering that stackNum is storing the exact same value which is in BoxedNum, but then why this is 8 bytes and stackNum is 4 bytes, this is because BoxedNum is not storing the actual value, but a pointer to the heap location where the actual value is stored. Then again, why 8 bytes? Because pointer size depends on the architecture of the system where it is executed. It is running in a 64-bit architecture. That's why it is 8 bytes. For a 32-bit architecture, it would have been 4 bytes. Now the next one is interesting. We have the boxed array, which is storing 1000 i32 values. So technically it should be at least the size of 4 multiplied by 1000, that is 4000 bytes. But since this is just a pointer storing the address of the location in heap, it is the size of same 8 bytes. So this BoxedNum and boxed array is not storing the actual data, but a pointer to the heap where the values are stored. And how much is the storage occupied in heap? That we are finding here using the size of function. A single i32 in BoxedNum takes 4 bytes, and the 1000 i32-bit array takes 4000 bytes of storage. We can also get the values from their respective storage locations. Let me add the print statements. Firstly, the stackNum is stored in stack, so we can use the variable as is to get the value. But for BoxedNum and boxed array, since they are pointers, we need to dereference them to get their values. This is possible because box smart pointer implements the deref trait, what I was explaining earlier. Now, if we run, we can see the values of stack num, boxed num, and boxed array printed. We stored 1000 zeros in boxed array, so there would be 1000 zeros. Technically, we don't need to dereference here because the deref trait and automatic trait forwarding allows Rust to automatically dereference smart pointers like box when you print them or call methods on them. So even without this, it will work fine. Now that we know how to use box, let's look at an example to understand when to use it. Consider we have a function called getNumbers. It takes a parameter called count, and if count is 2, the function returns an array of 2 elements. Else, it will return an array of 3 elements. In the main function, we are first calling the function with 2 and 3 as arguments, and storing the returned value in small list and large list variables, and print them. So when we execute this program, we expect the small list will print an array with 2 integers and the large list will print the array with 3 integers, right? Let's run it and check. We get an error. The size for values of type a list of i32 cannot be known at compilation time. So what is happening here? We know that Rust compiler should know the type and size of values passed during the compilation time. In our case, we have mentioned that this function will return an array of i32 values, but the size is not constant. It may send an array of 2 elements or 3 elements depending on the parameter. Realistically, it can even be a larger array. I've just taken a simple example to explain. In this case, what we can do is we can store the array in heap and point that heap location using box, and then pass the smart pointer as return type. So no matter how big or small the array becomes, the size of the pointer will always remain constant and would be known at compile time. So Rust can't complain anymore that the size cannot be known at compilation time. Let's run it and check. It prints both the arrays correctly as expected. There are multiple ways to create box. You have already seen the standard way using the new method. There are few other ways as well. Suppose you want to create a box of a particular type but don't want to assign any value. In that case, you can use the default allocation way to create the box. Suppose you want to create a box for string. The method we'll be using here is default. This means that the variable b points to an empty string in the heap. Default value of a string is an empty string. For integer or float, it would be 0. For boolean, it would be false, and so on. So we can print the initial value to check. We can even use pushstr to append to the string. And then if we print, we can see the final string stored in the heap. Let's run it to verify. You can see initial value was an empty string and the updated value as the appended string. The next way of creating a box is by using the into method. Let's say we have a variable called slice, which stores a string literal. Now we can box it using the into method. This creates a box for the string slice, which basically copies the string characters into a new chunk of heap memory. So we can print both box slice as well as the sliced values. Both should print fine. But this isn't the case for the string types. If we create a string variable, then create a boxed string using the into method, this actually transfers the ownership because the value was already stored in the heap memory. So once box is created, we only can print the boxed string, but can't print this another variable because it doesn't owns the value anymore. Let's run this one as well. You can see all are printed as expected. Every type in Rust can have the into method, so you can use it to create box for any type you want. There is another way to create box by using the new uninit method. It allocates memory space on the heap, but unlike the default method, it does not initialize with any value. allowing you to write data into it later to avoid double initialization overhead. It is used primarily in unsafe or low-level performance code, which is out of scope for us at the moment. So we'll skip this one for now. Another situation where we can use box is when we have the infinite size problem in Rust. Suppose we want to create the node data structure to implement linked list. In a node of linked list, apart from containing a value, it also contains a link to the next node. This node inside a node makes it a recursive data structure, and the size of a node cannot be known as it may be different from one node to another. This is the infinite size problem. So in this case, instead of adding another node, we can just mention a pointer to another node by using the box, since it has a fixed pointer size. So this makes the total size of the node constant and can be determined at compile time. This enables us to implement other complex data structures like trees and graphs. If you remember, in our video on traits, we learned the dynamic dispatch. There, we saw we can create a vector of different types, but all those types have same sizes. What if their sizes are different? Check this program. Here, we have a trait called draw and two struct types, one for circle containing a single f64 value for radius and a rectangle type with two f64 values for length and breadth. Then the draw trait is implemented for both the types. Now in the main function, we created a vector for these shapes using dynamic dispatch and tried to use the draw method to print them. If we run this program, we can see the error that the size for value of the dynamic dispatch cannot be known at compile time. The solution is the same thing. Instead of declaring the types itself, we can use box to pass the pointers. And in the dynamic dispatch also, we can mention that we are using box. Now if we run, we can see the output without any error. So to summarize, box is a smart pointer which stores data on the heap, keeping the ownership rules intact and automatically cleans memory when dropped. We have seen 4 different ways to create a box. We have used the box to pass dynamically sized data between functions. We used it to solve infinite size problem that helps us to implement complex data structures like linked list, trees and graphs. We also have seen how box can be used with dynamic dispatch. A limitation of box is that it supports only one owner at a time, making it the simplest among the smart pointers. For multiple owners, we use the RC smart pointer, and we can use ARC when there are multiple owners needed in a thread-safe environment. But these are not the topics to discuss before we learn multi-threading. So that's all about box smart pointer. If you like this video, give a thumbs up and let me know your thoughts in the comments. Subscribe if you like to watch more of such contents, and I'll see you in the next one.